Good morning. About 24 years ago, I gave a lecture in the very same auditorium on the occasion of Golden Jubilee of TIFR, and the Platinum Jubilee. Chairperson is Nagarajan. I think 30 years ago, I was the chairperson for the field exam committee of thesis. I think she was 20% student. Am I right? Yeah, good. Not bad memory. But parents are reversed. She was the chairperson. But you have a less tougher job, I suppose. Except that you caution me, I will have to start around. So halfway through giving a caution. Okay. Now, originally my topic was superconductivity, which I said well and good. I will do something on superconductivity. So took it without reservation. When I discovered, I don't know what went on in the environment. There's no one suspect speaking about condensed matter physics. Okay. So I felt it is my duty to see that the condensed matter activity of TIFR is represented reasonably. So I could do. Okay, I'm not sure I've done justice to the matter. Another thing, considering this kind of audience, I am also likely to be informal. I understand that this lecture is being broadcast live on YouTube. Okay, and I'm not very good at this social media business. So I hope nothing wrong gets broadcast. What I would like to tell the organizers is that for archival purposes, I'll be happy to provide every child the hard copy of whatever I would like to say with proper information, not that the archival material, and not this YouTube that whatever happened today. Actually, the ideal person to talk on this occasion would have been certainly some extraordinary kindness by the thesis, who has done extensive work. And Professor Ramakrishnan has made impactful work in the low temperature physics. Okay. What I've done, I will present and give a talk due to their personal commitments. So I will try whatever I can. I do hope for archival they would give the proper information. On an occasion like this, one likes to go back in time. And the first thing I went back in time was how I looked at 75 years ago. Of course, I was born before TIFR was born, and evident exists of that in my home. But I don't have a good archival section in my home. So I went to TIFR archive and found what is the oldest I can get, and that's what I would like to flash now. So that is why I was. The contrast is not good. So that's why I'm looking at. It reminds me of the then film hero Devanand. Okay, the next best thing is my oldest equipment. I do not know whether anybody wondered how old the equipment we have. As I said, I'm going to be a little random and so on. I said, I don't know whether I'm talking about condensed matter physics or reminiscing my old experience. To repeat of archival, I'll give a proper material later. When Golden Jubilee TIFR was trying to set up an archival section, they brought some nice museum like, that cupboard or whatever you want to put the glass thing and so on, put a bulb inside, and they are putting inside the thing of our annual reports. I felt that's not really archival. Since many things I worked with my hands, I never leave them. So a lot of old things were around me. I said, I'll give you. So one of the things I put here, I guess would be the oldest one with the earliest accession number. This is a hair hygrometer. It is there. These things I have kept in the backs of the auditorium fire, nicely hidden behind posters. Whoever is curious can go and have a look. And it turns out that except for 3 items, 2 glass blowing things and one given by Professor Mathur, a small ion source gadget, all else are put by me. of which I will show one and mention about another one. Then I was just trying to say this technique has gone wholesale outdated, because now you have electronic sensors and so on. I find that there's considerable discussion in the website on the hair hygrometer, and even suggested on school experiment for that. People who are curious can go and look at that. So in that one, I put a tuning for oscillator. Crystal oscillator didn't exist at that time. We made our own component counter. I will flash a slide of the person who was behind all these things, very, very important person. And I put 4 generation of the counters, the gamma ray counters. Someone was mentioning yesterday, all our computation went with punch tape, punch cards, but mine was even earlier. I had a punch tape also there. And at that time, I put one slide rule also, borrowed from Professor Mathur. My own slide rule, I have kept that. There was no calculator except that time. And all these things you can see there. Now let me see what next I do. Where this pointer works from here? Or where is the detector for the pointer, please? Yeah. Anyway, my topic, I said, nuclear physics of superconductivity. It so happened that much of the origin here centered around nuclear activities. One was nuclear magnetic resonance, even though there was no radioactivity, the condensation of nuclear exists. Then the nuclear spectroscopy, which originally was originated for looking at the nuclear decays, etc. I am happy that Professor Pill will be giving me a talk after that. So whatever I am messing up, he will clean up during his talk. And then it turns out that when they have this angular correlation and its effect with the internal fields, become a solid state tool. Then of course, Mossbach spectroscopy, about which I'll say a few things. Also a nuclear tool, but was extensively used for solid state investigations. And so that is a nuclear origin. And therefore, what I would do is I'll start with the NMR, because that was the fundamental thing. And then say a little bit about Mossbach spectroscopy, and then end my talk with 3 highlight contributions, because we said landmark. So maybe we are supposed to talk what are the landmark results that happened here. That is Professor Dharmati, and Hosur made my life easy by talking about him. Therefore, I'll skip this slide. This is from Vijay who followed Professor Dharmati. He built the first NMR spectrometer, I am told. Incidentally, Professor Vijay is still active and with his daughter at US, and he is in touch with me more or less on daily basis. Part of this part was directed by me, so to speak. So he made the spectrometer himself. It seemed that they got a mag from Switzerland and then used war surplus to make the electronics, and detected sodium resonance, and he was very happy that he could see the sodium resonance in sodium hydroxide. Now, this is a slide which is little distant I have put because of the early day. Again, Hosur yesterday remarked that the MRI was declared on this very stage. And it so happened at that time, the NMR people, this is Chaugli whom you are seeing, and Kasturi was there at the time. He was also interested in biological sample. They were already investigating biological sample using NMR. And then the Nobel Prize winning scientist, Lauterbach, he visited the section and he seemed to appreciate it just before his talk. And then in the talk, he declared his MRI. I think I saw a Google's write-up somewhere that his conference contribution actually was a poster to start with. And later on, seeing the importance, they convert into a plenary talk. Somebody can verify and confirm that this story is true. Okay, these are some of the early pioneers of NMR. Professor Gupta, Professor Malik, V. Nagarajan, he did zero field NMR. That is Chaugule, who was behind a lot of instrumentation and support activities in TIFR. At the earlier version, perhaps that 14 megahertz NMR spectrometer for the solid state investigations. Okay, this is a variant spectrometer which did a lot of NMR bulk activity. I have listed all the members of that time, okay. And since there was no other technique available, almost all of them were working on NMR for something or the other, the entire bunch. And the one which I put at the bottom, they were earlier and they left much earlier. DLR Shetty, V.S. Rao, Saraswati, Mungurwadi. B.K. Basu was working on ultrasonics because as a condensed matter, I just put it there, and many more I must have left out. Now, one of the earliest contributions from them was that one could see the s electron density at the nucleus, and then from there, then the polarization of d electron, and this, which in turn has effect on the s electron density. From there, one could detect the solid state property at the nucleus was an important thing in RPT5, and it is, I think, formed a part of Professor Malik thesis. And this was done under direction of Professor Vijayaraghavan. So it's a very, very important work. The next important thing that happened, because I am on NMRs, I am jumping and skipping in time, was the NMR in copper nucleus, where at that time our interest had shifted to rare earth intermetallics. And this was days of the rare earth valence of cerium, europium, and ytterbium, shuttling between two valence states. And again, its effect on the copper nucleus could be seen, and is considered the first such example of solid state valence fluctuation seen through NMR. Therefore, this is a well-received result from TIFR. I think this formed a part of Sambat Kumaran thesis. Now come the point of condensed matter physics. It is Professor Vijayaraghavan who really took a lot of pain and interest in trying to make this condensed matter physics. At that time, it was called solid state physics, because only part of the activity that it established well and grew up. He had an extraordinary knack of getting people together and manage them. It is a special skill, part of which I think I have acquired from him. At that time, since yesterday Professor Russo was mentioning, originally the group was called NEM, electron and nuclear magnetism. Then it got split into three. One went under Balu Venkatraman, chemical physics 1, one under Kanekar as chemical physics 2, and then the third one under Professor Vijayaraghavan as solid state physics. I didn't know when this department went, even though I was there. Pinto tells me it is 1997, when the then solid state electronics, and then we had a subsection called material science, and then solid state physics merged into the current department of condensed matter physics. Okay, since I talked of nucleus, I must also talk about my boss. I started my career in nuclear spectroscopy, and that was Professor Tozer, who are the head there. Incidentally, Baba ensured that he gets prominent people who all worked with Nobel laureate. Dharmate worked with Felix Planck, this gentleman worked with Kai Sigman, and one more, which as I move along, I will tell you. So this group was established to study nuclear spectroscopy, beta ray spectroscopy, etc. But then around 1958, Mossberg discovered the famous effect. I'll skip the other detail there. And then in 1960, I think, Pound and Repka used Mossberg effect in confirming the Einstein's relativity, that the redshift and the gravitational field. That really pushed the thing very high in the popularity. And then it so happened that 14 kV radiation of iron, commonly occurring element, and you have huge number of iron compound. So Mossberg spectroscopy became very popular, and TIFR being in the forefront, he latched on to the Mossberg effect and did a lot of work. Interestingly, one finding which I find is around 1961. That's here. Now I discovered that this 26 kV gamma radiation can give you a Mossberg resonance in 161 dY, was done by S. Jha. This is not our solid state physics S.S. Jha, but there was an earlier one. He later left for US and did some work there. Now, because this work resonance is so popular, almost everybody was working on it. You can see a lot of lists there. Dr. Fateh Ali, whom I joined. This gentleman, Prahalad Sastry, I will tell later. So we too worked with him. Girish Chandra had one, R.P. Sharma had one, H.E. Dabur had one, then K.R.P.M. Rao from chemical physics had one, which later on Date took over, which Hosur mentioned yesterday. Multan in material science. It's possible I might even left out one or two. K.G. Prasad, Vandana's boss, was working with R.P. Sharma. Now, I jumped disjointly because when I'm on mass bar spectroscopy, since I did a lot of work, I felt like reminiscing something about the equipment we had at that time. Cooling the sample was a problem. Ice was available. The next best was dry ice. Sargar Carbonics somewhere in Prabhadevi, we used to get dry ice and put chloroform or acetone and then go down to minus 27 or something and put the whole thermocol cryostat. BSF had just then come with thermocol. Okay, the whole, there's a constant mass per spectrometer mechanically moving. The whole thing will make a lot of noise and move till we manage with something. Then we had glass cryostat. I am sorry that I am not able to flash the complicated helium cryostat is at glass blower quilt. Incidentally, the glass blowing section of TIFR is a precious department of the institute. I do not know, the high energy physics people had told that the counters were made there. And these days, of course, the importance has gone down, except perhaps for sealing samples. I do not know how much work goes on there. I did take some photograph, but I couldn't incorporate in the one. And incidentally, there is one glass cryostat in the glass blowing section. I've asked them to preserve it. I strongly request that that be shifted to archives and preserved. Then metal cold fingers, flow cryostats, and so on. Two of them I show, which are one of them actually more important. Yeah, incidentally, this gentleman is my very close friend. He, in the early days, people, as somebody mentioned, came from DRC training school. Maybe I came and 2 years more training school input was there after they stopped. He is a very good electronics person. He automated mass bar spectrometer, okay, and even had this glass diwar automatically filling a small diwar every 2 hours or so. Okay, very brave man. Okay, it's a wonderful thing. The mass bar spectrometer had become a speaker. There is a counter there. We will not go into that. The other one was equally complicated spectrometer cryostat. This one. See, K.R.P.M. Long Telugu name, Kallakuri Mallikarjun Rao. This is an interesting personality. He was my close colleague. I do not know. Anybody recognize him? Nobody would write. I don't think anybody would belong to that category.
He came to SSC.
Yeah, he came to Salsa. Yeah, great. Good that at least one person remembers. See, so he is the one who was 3 years senior to me, Mr. Prahalad Sastry. He could do anything as a genius, very rational scientist. This cryostat was design was published in Nuclear Instruments and Methods. Wonderful thing. You see, there are 3 chambers. They all hooked together with metallic stainless steel wires anchored. Okay, therefore the heat conduction is extremely small, and then it will suck helium from the other end and come out from here. It sucks the cold gas and does that helium cryostat. The sample sits there, and then this for taking the helium in, there is a stainless steel tube. Okay, there are no tube benders available. The magic stuff was machined in the workshop. Okay, but much of the welding was done in our lab. He even made a stand for it so we can rotate. We had acetylene, gas torch, everything in the lab. Probably we did in the mezzanine floor. Okay, CM30. And the tube benders, what he did, he took filled the thing with water and dip it in helium, liquid nitrogen, it becomes ice, so it becomes solid. Then he bend it and then heat it up, the water melts off and use the tube. That is how the thing was done. Okay, wonderful technique. This cryostat I put in the archive, so you can have a look at that. It developed a cold leak in the center, so I couldn't use for helium work, but this was my workhorse for nearly 20-25 years till Professor Date left TIFR, and his cryostat, which I'm showing you the next one, that we used later on. This is another flow cryostat, but this was imported. And this also has some memory, some electronics for which was a bit known. And Dinesh Sharma, I'm very happy, is here. Was an accomplice in the later part of it, getting into microprocessors. Incidentally, like, I'm very happy to tell you that I grew with Intel. Intel started with 4-bit microprocessor, I think 8004 or something. Well, no, 4004. And then it was 8008, then 8080, then 8085, and so on and so forth. Charming memories. No tutorial, nothing existed. Everything was done from the manual. Thanks, Dinesh, for giving us that moral support. And here, there is a Mossbauer drive, which is not easy to see because of the contrast problem. And I owe this to Professor Pillai. I think if he's here next time, he will tell you. Because Devare brought a drawing from Groningen, I think. And then we machined it and constructed. Then I made some electronics. We one more slide, which I'll show you where you can see that better. And this became very popular. And many groups in India took that know-how. And I used to think I'm like Sankaracharya. There is a pitam in every part of the India, that south, north, west. Kashmir I didn't have, but it was there, including Professor CNR's lab. The other one, where Dinesh has a larger contribution. This picture is not for showing me, but this one, where I made the multi-channel analyzer. Incidentally, whenever these nuclear physics people do their nuclear spectroscopy, you have to see the energy. Therefore, to scan energy against intensity, they have what is called a multi-channel analyzer. The whole nuclear spectroscopy group had only one. And as you had seen so many names, all of them had to only one equipment. So they would go to BRC, read it, and bring the thing back, and then use that multi-channel, do that. And it will go from one room to another. Professor Vijay Raghavan used to call it, yes, that it is Dhampati, going from one husband to another. Now, we are using our all our Mossbauer data manually. I wish I had included that one. The process was to sit down almost the entire time of 10 hours and recording the thing. Okay, so if I have the permanent virtual material, I'll put that photo there. So we also used to sit late, and it so happened ESIL had made their first multi-channel laser. And that when this doping action takes place from one room to another room, it would break down. Okay. The engineers used to come and repair that. So I used to be with them and watch. Then I discovered what I wanted is a very small part of the whole thing. So I made my own, and that is sitting there. It was never enclosed in a box. It remained there. It served for me 20 years without problem. The triangle generator there, which was on a so-called prototype breadboard, it remained like 20 years. They all work. But the most important thing is the two wires going here and the socket here, you may not be able to see. I connected this. By then, TIFR across Cyber 360, and some of the labs got terminals. So there was a nice gentleman by the name Dosadai. Okay, he was accomplice. So I said, I will cheat the cyber computer by the keyboard signal. I break the keyboard outgoing signal, either it connect the keyboard or to my data. So I could directly transmit data to central computer. Perhaps that was one of the first computer automated experiment that we had. It's one of the charming memories I have. Now that Vandana has warned me, I'll skip to the remaining and push through. Now we had by then the most active work. We had all become sort of condensed matter physics. Ramakrishnan had many interesting systems called charge density waves. Grover got into vortex dynamics. Malikandar and a lot of interesting intermetallics and borides. Some of them I would like to say. Nigam also had a Mossbauer spectrometer. He made magnetoris, superconducting magnet. I would just like to flash through them. This is how the Mossbauer spectrum looks like. The x-axis is velocity, which represent energy. You can see the resonance happening. In this system, another important system from TIFR, which attract a lot of international attention, is a compound called European Palladium 2 Silicon 2. This also became part of Sampath thesis. Now, an equivalent thing which came from Malik group, but of a different variety. If you can just go back, here the signal simply shift with temperature. Okay, this the valency remains fluctuating, and what you are seeing is the resonance is the average of the two valence states. Okay, it just keeps fluctuating right down to 84K, which what you are seeing. But here, the valency is fluctuating, but it starts separating out into two separate charge states, and so much that at low temperature, this divalent even magnetic order. This was a equally interesting system, which had a lot of international interest. You can see Professor Dhar there. Okay, now that this, if you want to do superconductivity, you have to have low temperature. That origin came from Professor Girish Chandra. He worked in Moscow State University. I am not sure that because Kapitsa, I find is also Moscow State University. Whether he worked with Kapitsa, I don't know, but certainly he worked in Kapitsa's lab. And he was the first man to produce millikelvin in India. Again, it had a nuclear connotation. Okay, some bit of history. When I talk about nuclear origin, it so happened that it was Dharmati who started the asking for the rather ordering the first helium liquefier. There's an archival letter from him to Saha. January to 1962, he says that if they want to depute their person to see how the thing is being installed, they are welcome. The other one is equally interesting. He informed Baba saying that helium has been produced in the plant. So this for information. Baba says, I have seen it. Then he says for record, where it went, I don't know. But it's an interesting way the administration worked that day. Now this is the helium liquefier development here. The plant, I think I have wrongly labeled. The first plant was 3 liters per hour. The next plant they acquired was, I think, 10 liters per hour. The third one which you see is at 24 liters per hour. I think now they have 80 liters per hour flourishing. The important personalities I want to show here are Professor Nigam is here. The SC agronomy engineer of LTF. This is Sekura. I want to come and say something a little more about him. Professor V. Nagarajan. These people were the ones who were handling the thing in the most critical time in the late 80s and beginning of 90s. Really, they had a hard time. Those condensed matter phases would have, but they tried their best to do that. And when I take over, it is this Sekura who was really not the person for me to do that. If Nigam is here, he would certify as the importance of Sekura. I want to use this occasion to propose that I would like to institute an award in his honor for a good technical person of TIFR. Okay, please remind me on that. Other one which is currently there. Pardon? Yeah, I said that there's a mix up there. Actually, I want to put the Collins one, 3 liter, but it got shifted up. So all that will correct in your lecture. Yep. In fact, Pillai has been doing the same on everything and anything, let me tell you. It's a precious commodity in TIFR. Okay, this is how the helium progressed. Because helium has been sort of lifeline for condensed matter phases. We keep talking about helium. Okay. Okay, this is Professor Girish Chandra's publication, DA Symposium 1965, where he reports achieving 10 millikelvin. Okay, I don't want to spend much time there. Okay, you can see, all I can tell you is that it is detected by nuclear orientation, and the value he quotes are here 0.024 at this point. This is 0.01. Okay, 10 millikelvin. These are set up with Professor Girish Chandra used. They are there for a very long time, and that is the electromagnet which he used. Incidentally, the technique is called adiabatic demagnetization. I don't have time to tell that. In fact, much of physics and technology I will not tell because the time is running short. I must project what happened. People who are interested can come and talk to me, or as I said, I am hoping to document them in hard copy. So here is a cryostat which used to move inside the magnet, then they would magnetize it and then switch off the magnet. Incidentally, they have to do it very carefully, I am told. It may take about 10 hours in this case. In the case of Ramki and microkelvin, it takes 2 days to pull the magnet down. Okay. So I'm not getting into those intricacies there. And one man who can tell you a lot of stories about it, we should call him sometime, T.S. Radhakrishnan. I don't know how many of you have seen him. He worked with Professor Mendelssohn, the great man who has written a book and it's there in the TIFR. People should read that who are interested. Quest for Absolute Zero, wonderful book. He visited and he invited him to Oxford. So he worked with him. And it so happened he also worked with Prabal, who was a microkelvinian at that time, and Ramki also visited him. So anybody want to know the histories of how low temperature was in his time, in the late 60s, Radhakrishnan the man, I am trying to get him invited for a conference which LTF is organizing. Now I am on to business now quickly. Some of the important thing that did, Professor Nigam made the first superconducting magnet. I think it is how much? 5 Tesla or 6 Tesla. Okay. And the thing is, it was hard work. I believe Pillai also would know, because after him, I think they also made 1 kilometer of neobium titanium manually wound. You have to wind it tightly, otherwise the windings will shift around and quench the magnet. But it was used and a lot of work has been done. Since I am supposed to show some physics also, I flashed this one. This lady is my colleague at Mumbai University, Radha. You may not know, I do not know whether she is in the audience. Yesterday she was there. Okay, the important thing as a piece of physics, later I'll talk about the so-called borocarbide. He can see this one, the superconductivity goes up, so to speak, and then trying to die down and then again pick up. This is so-called re-entrant superconductivity, and that is what made this system bit famous, about which I'll flash a slide again later, hopefully. This is my friend C.R.K. Murthy, very, very important man for me, because I cut much of my thought processes discussing things with him. And he was a geophysicist who shifted to condensed matter physics because he was on rock magnetism. He made his own equipment. He worked with Blackett, early persons again, Professor Homi Baba sent him to London to work with him. And I put one of his equipment in the archive, I think, and see. Professor Grover, if he is here, would know that he used this equipment.
Did not work with Blackett, he worked in
Correct. No. The Blackett came, sorry. The Blackett was the inspiration for the whole affair because he was interested in continental drift. That was the idea, paleomagnetism. Grover, so you know, C.R.K. Murthy's your lecture is already over, so you may correct it in the hard copies, anything more.
that in Khandala, which everyone wanted to visit.
Wonderful, yes, he is equally known. And there was some Pandu who used to make good upma, that much I know.
Yeah.
Okay, then come the STC. This is, I do not know whether I mixed up my slides. You may see it a little later. 1986, this high temperature superconducting revolution came up, where superconducting discovered at temperatures of liquid nitrogen. So people thought that everything going to change and a lot of money was being spent. Rajiv Gandhi offered 100 crores and Professor Siyanara was the chairman of the funding committee. It was split into two. Professor Ayangar was the chairman of the applied committee and Professor Vijayaraghavan was the chairman of the basic science committee. So a lot of money flew into TIFR. At that time, we acquired some equipment. So let me see whether I have those photographs here. Yeah. So we got a squid magnetometer of 5 Tesla, vibrant sample magnetometer at 12 Tesla. Then we have a PPMS, physical property measuring system, which could measure everything: AC susceptibility, heat capacity, resistivity, and maybe thermo EMF and so on and so forth. There was also a closed-circuit refrigerator for AC susceptibility, which is missing in the slide. I don't think Professor Paulus got it out of the STSC funding. But since I couldn't get him in my sequence of event, but he had a dilution temperature much later, out of which a wonderful quantum Hall effect was result was produced. I think Professor Arora would mention in his talk. Okay, I may flash the result there. Yeah, beautiful. You can see. Okay, here comes Grover. He dedicated his life to vortex dynamics. He was in Japan. I think Ito dedicated one instrument to him. Was very happy because in TIFR would get turned once in a month. We had only one speed at that time. And he did work. I'm not really competent to comment everything. But what I want to present here is the amount of detailed work that Grover and Ramakrishnan did. See here, the number of points. I think they are all taken. I think every, maybe next one has a slide, 0.1 millikelvin accuracy, and every 10 millikelvin they had a point, something of that kind. Okay, see here, this one you can see the reduced temperature range, 98, 97, that is just within 1% they cut, and then got this so-called purifier, out of which they would say how the vortex lattice is melting or solidifying and so on and so forth. This is what they said. They said they discovered Nelson's laws. See, this is a phase diagram, and that I do not know whether Grover could correct me. It goes from liquid to solid, and then it goes one way, and then again it returns back. So this is a so-called reentrant business, which was a critical requirement for the existing theories then. While I'm at it, I want to talk about this two slides on material science, because a lot of activity went on at that time. Professor Multani started along with Patankar and my friend Shastri, whom I was saying. Okay, the Shastri end, actually, I skipped. I would like to use this occasion to say that he did a variety of things. He did Mossberg spectroscopy. After it, he said, no, I want to change over. Then I think he went to here. And then he said, this is not enough. Then he went to solid electronics. There he tried to make a calculator. I was accomplished for that. We had a calculator about a rack long. Okay, we did many things there. By then technology changed. DCM came with their computer calculator, and then went off. Then he went to ESIL as a consultant for that. Then he went to Zambia for about 2 years on a teaching assignment. He came back as a Guruji. Finally, he's a full-fledged Guruji with international following. He has a institution called Devipuram in Visakhapatnam. Unfortunately, he passed away 3 years ago. But there's a big institution there who are religiously inclined. They can go and see the film. The puzzle really for me is that how come a totally rational scientist could go totally differently spiritual and so on. And I tend to believe maybe there's something spiritual there. Okay, Vandana is further warning me. Let me rush through finally. Okay. Okay, now here is my the outcome of the material science. Since I am supposed to be on superconductivity, my present colleague at CBS, Sangeeta Bose, whom many of you know, Bhushan student, she worked on this fine particles and showed that the type 1 and type 2 behave differently when you make them into fine particle, about which I don't want to get in now. Now the finally will make maybe 2 minutes each on the 3 landmarks, because it's a landmark one. Director, I think at the time it was Sandeep Trivedi. He mentioned a lot of landmarks. In condensed matter physics, he mentioned 2. One, a work which with I was associated, the so-called quaternary borocarbide. Other one was the discovery of superconductivity by Ramke at 005, about 500 microkelvin. Sampath Kumaran, extensive work, okay, enormous work he had done, and he informed me that this compound is gaining international prominence. So I would like to say a few things about that. These 3, and then wind up. That is Sampath Kumaran's lab. He states that in this material, this is a comparison material, you can see an Hall effect taking place as the temperature is reduced. When the field is 0, the resistance goes up, inside now the resistance would come down. When you apply the field, the resistance comes down like a metal. This is like a superconductivity. When you have superconductivity, you have something in the heat capacity. When you apply field, superconductor is killed, it behaves normally. It does something crazy like that. And the net result is he got this anomalous Hall effect over this field range, okay, at 4.2 K. Now, this was somewhere in 1998, I think. Now, 2019, there's a paper on this very same material in Science, claiming that they have found topological Hall effect in frustrated triangular lattice magnet. The net crucial observation is the same, which I will flash in the next one. Yeah, you can see the similarity against magnetic field. So somebody strongly feels that he should get the recognition for discovering this aspect, about which he has sent a Condensed archive, which I reference, I have put there, you can see later. And the other important thing which I have done was discovering a material called terbium-2 barium cobalt oxygen 5, where we find this is temperature, this side is dielectric constant, and each one you are applying a field. You have a ferroelectric material which respond to application of magnetic field. These are called ferroelectrics, and this is happening at the highest temperature, and therefore he believes this will be an important material for application. These two must be noted. Now, there is a bismuth work of Ramke. How much time, madam, I have? 5 minutes. Chalo. So, the important thing is here, Ramke's work, I call it as a complete science, because number one, he proposed the problem, he devised the technique to solve the problem, and solve the problem also. So, the entire thing he has done, and as I told in his farewell function, it really requires a lot of courage to sink that much money, that much time, that is effort. You must spend about a decade just trying to achieve the microkelvin, which itself is an achievement. And then having done that, put bismuth in that, and then go and get measure and establish. Fantastic work, let me tell you. I will skip this slide because too many things there. This also I'll skip. This just shows the complexity of the setup. Okay, what are things sitting there? You have to have a 1K you achieve. Incidentally, he achieves the millikelvin by standard so-called dilution refrigerator. The remaining are designed and developed by him. You achieve the normal millikelvin or the other one, Girishchandra one, I said adiabatic demagnetization. We use a paramagnetic salt. Here we are doing adiabatic demagnetization on nuclear magnetic moments, okay? Nuclear magnetic moment. It is there they get cooled. Now the nuclear temperature should go to solid state temperature. That's a problem by itself. And he waits for, I think, 2 days before the solid can really get cooled. These are all technical detail. I don't want to get into that. He achieved 39 microkelvin. Fantastic thing. I think world about 4 magnets are there. 2 of them may not be working. So in that sense, we should really be happy that TIFR is doing their basic work. Now here is a basic result. You can see the superconductor occurring. Okay. It's about 0.5 millikelvin, 500 microkelvin. Simply getting a resistant drop incident, this is susceptible, not resistance. Okay, diamagnetic circuit you are seeing. Simply seeing a transition is not a proof. It should respond the way superconductor would do, which you do by applying field. Okay. Now, the other important thing you should see here is see the amount of field he is putting 4 microteslas, particles. Okay. I hope my number is right. And then there's such a small field, and you can see the thing shifting. And if you want to have an effect of this field, even the earth field should be shielded. So shielding magnetic field itself is another crazy thing in this setup. And he did all the thing. And what is the impact? He says that normal metals have roughly like 1 free electron per atom. Okay. In this case, the carrier element is so small, there's 1 electron about 10,000 atoms. Okay. The electrons are too few. For superconductivity, the electron must pair up. Such low density, 1 in 10,000, will they talk to each other and produce superconductivity? This is a question mark. So that is a problem which he has posed to the world. This is what it says. The results mark a new episode in the history of superconductivity. This is the editorial comment in the Science article. So now I come to the final one. I kept it final because even if it doesn't say anything, nobody is going to complain. So there's a lot of teamwork. And Professor Gupta suggested that we should work for the series of rare earth nickel for boron. And then we went into the whole business. Now these are the two students who really worked hard for that. This Chandan Majumdar, he is now a professor at science and nuclear physics. He is a professor at IIT Kanpur. He should have got more reward than what he got, but somehow field being what it is, it didn't work out. Part of the fault might have been mine. My favorite on this thing is just I said that the business superconductivity had its own structure of science. I gave this talk once or twice. I tell them this is a classic case of a scientific discovery is made. I'm not going to tell all of them here. I only tell the steps. Choice of a favorable system, luck, systematic hard work, experience, literature survey, conjecture, verification, consolidation, killer instinct. Our friend Ramchandran Baji, I believe, will be here. He is the one who wrote this saying that TIFR lack killer instinct. That story is later. Progress, birth of a subject. The work had all these components, classic case of, but then I'm not going to talk about it. What I'm happy about when I wrote this article in Current Science, editor seemed to have taken a note of it and he remarked in this editorial comment. So there is some truth in that. Now I'll quickly flash one or two slides and wind up. Okay, so this is how the whole thing started. We are measuring that one. We got a small cut here, but not zero. Susceptibility had a small variation, but not diamagnetism. When we went into low field, there was a diamagnetism. We said there is some superconducting signal, but we did not go into zero, what it is. So we went after it. Everything we should do, repeatability is important. We tried 4 samples. We did get them. But the interesting story is here, the first sample had a much larger dip, 1 to 0.7. Other guys are only 5%. Why so? I will not tell you now. This is for a graduate student lecture. Heat capacity is supposed to have a jump across the TC. Nothing happened here. Okay. Leave it at that. I hope people can see who are the authors. We went after it. I tried to crack what the problem was. Made all sorts of alloys. I felt it's an impurity. In 3 samples, we got this small signal, but still result was not going to zero. So I felt that the thing might be something else. I guess it could be carbon. Why I guessed, I will not tell you now. How I got the carbon also is an interesting story. I will not tell you now. So once I put carbon, the result went to zero. Okay. So that was the proof that I got the thing solved. The final proof, you can see now the heat capacity anomaly in this sample becoming much larger. So we knew that the compound is YNA2, but we could not figure out what boron and carbon. Bell Lab corrected 3 months later and found that compound to be B and C is 2:1. So they made the compound YNA to B2C. Now you can see the heat capacity jump going more. And when you make a single crystal, it becomes a classic superconductor with a straight jump, and you can do other calculation as well. So YNA to B2C was the one. Bell Lab made the whole series. They really made an impact. So there was so much, it is and the famous ITC case, the first transient temperature reported Bednar's and Miller's for 39 Kelvin. Okay. Nobody noticed for about a few months, somebody picked it up and then it went to more than 90. The record was around 135 and the pressure 165 and so on. So anything new which is coming up is exciting. This phase replaced nickel by palladium. It went to 23K, which was highest for metals at that time. So nature said, with a new route to high TC. And then that became a whole news. Everybody went helter-skelter. All metal physicists went about melting sample. Now, as I said, this is going to the end of the step, which is called a birth of a subject. It found all sorts of things. I think about 40 compounds it forms with all sorts of properties. This is a list of compounds which others made, not we did not make it. And then the other interesting aspect was that this thing produced 3-4 compounds which are so-called magnetic superconductor, which I told you the re-entrant part. Okay, so the Physics Today article that this being a 5 box for that, and then we had an international conference, NATO, to what should I say, compensate for the killing in war. They also hold scientific conferences. One was held on this discovery at Dresden, that I believe was really a climax for it. And now I'm coming to the last slide. So with that, I finish that one. I must mention something about the present one, which I learned from Professor Hosur yesterday. I listed the present, the bunch of people from the department, from the website. All I can say that I find that they are exploring new lands, and my best wishes to them to make new landmarks. Thank you, friends.